Okay. Uh, hello. Good afternoon and good evening, everyone. I'm Jeong from Yonsei University, and I'm going to talk about finding optimal threshold for quantum error correction codes. For first, the motivation for is that quite a portion of the quantum error correction research focus on finding accurate and sufficient error correction codes and the decoders for them. So the first questions are how do we decode, and if there exists some kind of accuracy threshold. The accuracy threshold is where the error correcting system works and fails. So below the threshold, the probability of the decoder of success will be 1, and over the threshold, it will be go to 0. So re more about this is that first we can encode error correcting. We want to encode information 0 and 1 into repetition code like 000 and 111. Then we can get fault tolerance due to bit level errors like 101, 010. Then we can decode by the Moser vote in the classical settings, but for the quantum settings, we cannot do that because the measurement itself will destroy the quantum state. So we use the syndrome measurements for the measurements, and we use the information to decode our syndrome measurements. So that was a little bit of recap. And so in this classical setting, you can intrinsically see that the threshold will be about 50% for physical error rate, biological error rate. That that will mean that physical error rate goes over 50%, the error correction system will fail. So the optimal threshold is that how the optimal threshold is the theoretical threshold of the error correcting system that will work that will be found by the statistical mechanical mapping. These questions will be answered for the stabilizer code subjective Pauli noise, but it can be done in the subsystem codes. So there were lots a line of research on the topic from the topological quantum memory on the 2D codes and deploying noise and correlated noise. And recently, there has been some research on correlated noise for 3D codes. The example for today will mainly focus on 2D codes on deploying noise. So the third code looks like this. It'll be array of data qubits and SLM measurement qubits in the lattice with periodic boundary conditions that will make a torus. And the stabilizers will be encoded in like the plaquette and star and the face and the vortex of this lattice. So those stabilizers will commute with the system, will commute with other stabilizers, and the stabilizer will act trivially on the quantum state. But the logical operator, like you can see on the right, that will be a state operator that acts non-trivially and commits with all the stabilizers. Like if you have a 000 in the edge of the lattice, the logical operator will change the encoded the qubits to 111. That will change the logical information, but it will not give any syndrome measurements. So it will act non-trivially, but the state couldn't recognize it. So that was a little bit about the Turk code, and I'll explain about how to decode them in maximal likelihood. First, the first idea is that we have to know the error state, the error how the most probable errors. So if the error is uh, independent, there will be some product of individual errors, and if it's correlated, it will be represented in some functions. So want to find the max of the probability error state, probability of the error state. And on the third code, there will be about three situations. The first one will be the syndrome. A syndrome will be uh, a boundary of some regions that will be a product of stabilizers that will act trivially on the code, so we cannot detect them, but we don't have to. For the third one, that will be the product of a logical operator with some stabilizers. So that will act non-trivially, but it will be undetectable. That will make a logical error. The most situation that will be focused on will be the second one. That will be uh, error with open error shades. Like the red will be the syndrome measurements, and the blue ones will be the errors on the edges. So the simple idea, one of the best idea was the minimum weight perfect matching decoder. So we can make a closed loop around the situation two. So for the left plot, you can see that the above situation will correct in the yellow lines. So with the blue and yellow lines, they will make a non-trivial loop that will make a logical error, and the blue situation will make a closed loop that will fix the error. So the intuition in that will be that we don't have to actually know the exact error chain, but we only have to know the uh, error chains that will make a closed loop that will make a error class. So in in this in from this intuition that will we can make some error classes that will be about four. The first will be the trivial ones on the error chain, and the second, third, and fourth will be the error chains with the logical operator. So we can divide the situation into four classes of errors. So the first idea changes into finding the most likely error classes. For the figure below, you can see that the most likely error situation will be class 3, but the overall the probability of the error class will be the class 1. So we want to find the most likely error class. And how do we can uh, we can encode the error class into some kind of some constant error, the fixed error, and its fluctuations by the stabilizers. That will be mapped into a Markov process. Then we can approximately calculate the maximum likelihood for an error class. So for a fixed error or constant error E, the fluctuation E prime is this. So we can add some stabilizers to the original error chain, and it will make some fluctuations. So for E and E prime, that will make a closed loop. That will be the same error of same class. And for E double prime, that will make a non-trivial loop. That will be a different class of errors. We call the original E quantum error chain and E prime fluctuation error chain, but the original quantum error chain will not be imported because it'll go into some kind of partition function and will be erased. So the Markov process is that we can get some kind of quantum error chain in the initial step, and add some stabilizers and make a fluctuation error chain with the Markov process. Markov process means that the future state probability will be independent of the prior states. So it's not a related probability, but like a ratio of the probability will be look like this, where we can find the original error chain E with the probability of P and 1 minus P for the all edges, with, where the edges what will be in the error chain will be go to P, and for the edges out of the error chain will go to the 1 minus P. So we can represent the probability of error like this. And the ratio will be goes by this like for E and E prime. So the ratio will be a product of 1 minus P over 1 minus P. And the 1 minus P over P over 1 minus P will be less than 1 because the probability will be less than 0.5. If the probability is over 0.5, the qubit is encoding not any information. It's not encoding any information. So for the edges, qubits in the C and E, the probability will go down, will increase because it will be a product of -1, and the decrease for C, but not E. This like a bit of an equation around here, but it is not important. So, as we've seen before, we can map the ratio of errors in probability, and we can make a classical spin model to encode the error class. Until here, do you have any questions about this?
I was wondering if this is published.
For the this is mostly based on the Bombin from the paper from Bombin. It is the name was Strong Resilience to Depleting Noise. It's well published and is there. There has been some literature on this subject.
Thank you very much.
Okay. So on to statistical mechanical mapping. We can make the stemma mapping on the random bound Ising model for some constant error chain and fluctuating error chains. So the Hamiltonian will look like this. Will have spin Ising spins, and we have some nearest neighbor interactions around them. So, and the partition function will look like this. It is textbook information. So. And the quantum error chain will be quantum error chain. The edges will have 1 and -1 with if the qubit has errors will be -1, and if don't, we can encode it in 1. So what we can do is that we can find a phase transition about that in the Ising model to find the optimal threshold. So in the previous slide, we have map the probability into a ratio of errors like this. And we can encode them in the Ising model with the partition function. That is the assumption that the exponential minus 2 beta j dot tau ij will be the same as the probability 1 minus p over 1 minus 1 or power of 1 minus 2 and NLE. That will be explained into some slides later. So we can make the ratio of probability into a random Ising model Hamiltonian. So, and we can in the partition function, you can map the probability distribution like this with the Hamiltonian and the beta of the temperature of the system. But without the assumption this will be just a random Ising model, but with the assumption of exponential and the probability, it will map into the what create a quantum error correcting system. That will be the condition of Nishimura condition. The Nishimura condition will signify in the probability and the temperature of the random ionizing system. That means that for some temperature of the Ising model, it'll act same as the random Ising model will act same as the quantum error correcting system. And the left plot will show the Nishimura line. The solid lines divide the disorder phase and order phase of the random ionizing model, and our quantum error correcting system works on the Nishimura line where the assumption meets. So you can find the optimal threshold where they cross, like those in P1, P0. So you can map into a randomized model, and the situation on the Nishimura line will work as a quantum error correcting system. So it is so summarizing the results, the stabilizer codes and the polynomials will be mapped into the disordered statistical mechanical model. And we can find the optimal threshold by the phase transition of the Stedman model. And we can map the maximal likelihood decoding problem into calculating the partition functions. And the bit in intuition with the physics will be that we for the uh, bit intuition is that we the disorder phase and the order phase will be divided by the free energy, the domain wall free energy. The delta will be the difference of the domain wall free energy. And you can see that for lemma 1 is a below threshold. The domain free or wall free energy will go to infinite. That will make an order phase where the logical operator to make a logical error, we need an infinite amount of free energy to make a logical error. And for the below threshold, for above threshold, the logical operator, free energy of the logical operator will go to zero. So that will make a disorder phase. The idea will go beyond go on to the Earl Campbell's doctorate thesis that has self-correcting properties and single-shot decoding probability of the quantum error correcting system. That might I might make some slides in with some chance. So. In the Turing code with the deploying noise, we have two lattice for X stabilizers and Z stabilizers. The red lines will be the Z stabilizers with X errors. The interaction will be on the red lines. For Z errors will be the blue lines. And the Y errors, which will be a product of X and Z, that will be seen as the green errors with the crossing lines. So if we do the multicolor Markov chain multicolor, we can see that in the order phase, the magnetic the Ising spins are all aligned to 1 or -1. But in the distorted phase, you can get the Ising spins will be all disordered like this. So you can find the phase transition about 0.18%, about 18%. The left will be the minimum wave perfect matching decoder with the deplacing noise, with independent noise. That will be the threshold of 10%, but with deplacing noise, the threshold will go up to 15%. So we can see that the minimum wave perfect matching almost meets the optimal threshold about 18%. So we can do quite well only with the minimum perfect matching for toric codes. So that was the example of toric codes with displacing noise. And for correlated noise, you can map into the Markov chain into the measurement errors. The measurement errors spans as the measurement happens. So as in the plot override, with the correlated errors, the optimal thresholds decrease. So this was the paper for correlating noise on the 2D codes. Okay. Uh, any questions so far?
Can you also map different stabilizer codes to statistical mapping? Like for instance, I believe the Ising model is the simplest phase transition model. It's the simplest Hamiltonian that shows phase transition. So I believe for more complex codes, you're going to need more complex mechanics model mapping. So is that true, or is it Ising model fairly universal for quantum error correction codes?
It can be done on stabilizer codes and subsystem codes. And for like GKP codes with stabilizers, that can be done, but there has been no research on those. So uh, it's quite a hard problem to solve. So that there has been not much of a research on the subject. So yes.
So I have one more question for Ising models. For Ising model with dimensionality 4 or above has no phase transition points. So is that also true for toricles? Like for
Yeah, that's one of the interesting thing about the 40 Torah codes. The 40 Torah code is a self-correcting memory. That means you don't need like a active a decoder for the correction. So for 40 Torah codes, you can do self-correction, but 40 Torah code implanting the 40 Torah code in actual hardware is almost impossible. So we are looking for uh, somewhere in between, like 3D Tor codes or 3D private tricycle codes that have a little bit of self-correcting property, which we say a single shot decoding property.
So toricles above 4 dimension has no self-correcting properties. Is that correct?
No,
Yeah.
it has self-correcting
Yes,
property over 40, yeah.
but making it will be like physically impossible. Like in
Almost
your
impossible is
yeah.
theoretically possible, but yes.
So in this work you talk about the polarizing noises. Can you also do it for like other noises like dephasing or like amplitude damping channels as well?
Mm, the topic mostly this is just the third code works on the polynoise, so those noise will cannot be mapped into statistical mechanism mapping, I think.
So you can do it for dephasing noise as well.
Mm, we can make a approximation of dephasing noise with the polynoise, so it can be done, I think.
Okay.
Any more questions? We'll go to the future direction of the subject. So it has been done for 2D Turk codes or 2D color codes, but it has but for recently the QLTPC codes are dominant of the source of the research because it can be mapped with the high logical rates. So the idea was our idea for this was that uh, we can tailor the stabilizers X and Z into XZZ X surface codes. And with this kind of stabilizers, you can make a line of stabilizers that can be mapped into 1D repetition code that has about threshold of about 50%. And for the 3D turret code, you can also do this for the 3D turret codes as deformed surface codes. So the 3D turret code has a threshold of about 6% for BPOSD for deploying noise, but if it is deformed, you can make a threshold of about 50% for bias noise. That'll be only errors for Z errors. So the idea is that we have some leftover threshold capacity for the 3D turret codes. So it can be done with the statistical mechanical mapping to find a high optimal threshold. That was the idea. Then you can fully utilize the error capacity of the codes. So the research focused on flagging the other researchers that we can make a better decoders for 3D turret codes. So also for bicycle codes, the pseudo threshold is very low, so you can make a statistical mechanical mapping also on bicycle codes and make a high and find a high threshold for bicycle codes. That is for the future direction, and there may be some interesting high order dimension, high order QLPC codes with high optimal threshold. Uh, that was all. That was all I will deliver. Thank you. Any questions?
So you said that the BP, the blip propagation, is a general decoding algorithm for LDPC codes, but is like BP like fast enough to do implementing in like real time or like within the frame of megahertz?
It has been there has been some has been uh, saying that BP is sufficient for real-time decoding for like relay BP on BB codes, but the actual experimental paper hasn't come out, so we don't know. That's what I know. So,
Is the pearl, is that like Judea pearl?
come again?
The
Uh,
pearl, yeah, A2. It's like a
uh,
causal solution.
uh, you're saying that this paper is I didn't understand you. Could you come again?
Oh, I was just wondering, if it was like related to some kind of causality paper. Is it like Judea pearl? Like who's the author?
Uh, I have to search. Just a sec. But it was not a quantum paper. It was saying that the classical LPC codes can be decoded by the Belief propagation. Yeah.
Yeah, I was just wondering if it was Judea pearl, like the causality
Uh,
person, belief propagation guy, maybe
if you
the
know
author.
BP, you'll know better than me. I don't know what you're talking. I think.
I believe he's asking about the author of the paper. Like who's the
Exactly,
author?
yes.
Yeah.
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 So, uh, uh, I don't know the full name, so I I can I can't answer the question, I think.
Okay, thank you.
Uh, Jude Pearl, you said.
Oh, okay. I think I
Yeah, yeah,
know.
yeah,
Okay,
yeah.
thank you.
So no more questions, then I'll stop right here. Thank you.